Now let us try to understand the weight initialization process. So weight initialization is very useful in reducing the chances of vanishing and exploding gradients. The major concepts behind the weight initialization is to minimize the difference between variance of input layer, number of parameters of input layer and output layer. Means the difference between variance should be minimum. If you are able to maintain that minimum difference in variance, then network will be stable and learning process will be stable. But the weight initialization process which are used to achieve this generally depends upon the type of activation function we use in the network. For example, if we use the ReLU activation function, then we use Hay initialization. So in the case of Hay initialization, it uses the concept of numpy random.rand to generate Gaussian random numbers between the range of size of network at layer L and size of network at layer L minus 1. Now to achieve the variance, we multiply it by using square root of 2 divided by size of network at layer L minus 1. So this is the process to achieve the weight initialization process when we use the ReLU activation function. Now another thing is, suppose in the network you are using 10H activation function. So in that case we use the Javier initializations. There are two different variations available. So in the first variance, what we do, we take the random number generator, we generate the Gaussian random numbers between a range of network at layer L and size of network at layer L minus 1. Means size of network at layer L and size of network at layer L minus 1. So between this range, it generates the Gaussian random number. We multiply it by using square root of 2 divided by size of network at layer L minus 1 and plus size of network at layer L. This is to achieve the achieve the variance. Now the another version of this is, in place of this, it only multiply it by using square root of 1 divided by size of network at layer L minus 1. So this is the process of weight initializations. So from the discussions, you may start thinking that this entire weight initialization process is highly dependent upon the ReLU 10H. Similarly, when the activation function will change, the weight initialization process will change. So it is a continuous process, and these days a lot of new weight initialization process came. So in the separate lecture, I will try to explain what are the other weight initialization processes are. So now let us move towards the next topic. Hello, let us try to understand the concept of gradient clipping, which helps us in avoiding the situation of exploding gradients. Generally, we do not apply gradient clipping for the scenarios of vanishing gradients. So, we achieve the gradient clipping by using two different ways. By using some threshold. So, suppose our gradient G, if we represent it as norm, is greater than any particular threshold value T. So in that case, what we do, we apply or we replace this gradient score by T. So we use some pre-initialized threshold and then we just use the value based gradient clipping. So in that case, in the entire back propagations, if in any case in any weight updation process, if we see that our gradient value is greater than this threshold, we just put this gradient value equal to this threshold to avoid the scenarios of exploding gradients during the backpropagation. Now the second strategy is used, known as backpropagation using norm. So we use the norm of gradient g, and if this is greater than a particular hyperparameter, that is c, then we apply a norm based gradient update where this part is an unit vector. This is a gradient, this is a norm of gradient, and finally the combined part is a unit vector. So this arrangement makes sure that even if its value will be unity, the gradient will have value as c. Now how this c is different from this threshold? Actually, to select the c, we use some initial epoch and check the statistics and norms of the gradients, and based on that we identify the most stable value for this hyperparameter. So that's why it is different from this thresholding based process. So gradient clipping this way helps in backpropagation and avoid the scenarios of exploding gradients. So now let us try to understand the batch normalization. Actually, batch normalization is also helpful in solving the issues related to vanishing and exploding gradients. It actually works at each layer. So for each layer, it actually normalizes the layer's input by using recentering and rescaling, and makes the network stable and also faster to train, and that's why it reduces the effect of exploding gradients mostly, and little vanishing gradients also. So in the current scenario, suppose B is the mini batch of size m, so we can calculate the mean for input x, where x is our d-dimensional input vector. Similarly, we can compute the variance for our variable x, d-dimensional input vector x. Now, for each layer k having dimension 1 to d for input x, we can input vector x, we can compute the normalized activation value by using xik, where I is representing the size, I is representing the batch from 1 to m, because we have taken the mini batch of size m. So for each batch we are taking the input variable and then subtracting the mean, and then dividing it by using the square root of variance at the same layer, and then adding some constant. This constant actually helps to get the numerical stability. Suppose in some cases if we get a zero variance or something kind of scenarios, so this will give the normalized activation value for each of the layer, and by using the values at each of the layer, normalized activation value at each of the layer or at layer wise, we generally counter the exploding gradients scenarios and sometimes the vanishing gradient scenarios.